In the previous video, we worked example problems where we were given a function and we found the first 4 non-zero terms of that function's Maclaurin series. And so what we're doing for this long, tough section on Taylor and Maclaurin series is each of the example problem videos are going to increase in difficulty and complexity. So now in this video, we're going to be given a function and we want to find the actual Maclaurin series representation for that function, not just the first 4 non-zero terms. Okay, so again, we're still keeping it kind of simple. It's just the Maclaurin series, so centered at 0 for each of these functions. And we're not going to be going the additional step of proving that the function is equal to the Maclaurin series. We're just going to be doing, so the way I had written it was, instead of drawing an equal sign, you draw an arrow just to indicate that we haven't proven that they're equal. This is just the Maclaurin series for the function. Okay, and also once we get the Maclaurin series, we're going to find the radius of convergence as well. Okay, now you might look at this problem here and think, well, this is kind of a parallel to the binomial series. We could get the Maclaurin series from the binomial series, but we're practicing finding these series from the definition of Taylor series from scratch. Okay, and so here's the main theorem. So if a function has a power series representation at A, that is, okay, so if it does, then the function is equal to, and here's just the standard form of a power series, but the C sub n is as shown here. It's a standard power series, but with the C sub n's defined by this. If you have a power series centered at A, and the coefficients, each coefficient is this, then that's the power series representation for that function. But again, we're not going to be proving that they're equal. We're just going to be doing this step and then finding the radius of convergence. Okay, so the way to approach doing this, building a Taylor series or Maclaurin series of a function, is you make 2 columns, make the left column a little bit bigger than the right column, and in the left column, we're going to write out the function, and we can write it like this too. And then we're going to write out some of its derivatives, as many as we need, so we can, the idea is we want to identify a pattern. Okay, so the second derivative, bring down the minus 2, 1 minus x to the minus 2 minus 1 is minus 3, but then don't forget the chain rule here, so the derivative of 1 minus x is minus 1, so that's going to actually make this a positive 2. Okay, now just note that it's easy to get confused and think that in this step here, this is supposed to involve the center point. So let's say we were doing this, creating the Taylor series centered at 2. It's not like we would be saying, okay, f of x minus 2 is this, then f prime of x minus 2 is this. No, this step doesn't involve the center point ever. And you can think about it like, so if you look here, okay, you've got the function. So like if we were doing the Maclaurin series of e to the x, it would be equal to a summation. If we were doing the Taylor series centered at 2, then it would still just be e to the x is equal to the power series. See, the e to the x doesn't change. The function doesn't change if you're changing the center point. It's still just the function is equal to the power series. The center point comes into play with where each of the terms is going to have the x minus the center point to the n power. And it does show up with the derivative of the function, but we're just going to be plugging the center point in to each of the derivatives. Okay. So, all right, so we bring down the minus 3, it's minus 6, but then we do the chain rule and we get a minus 1 factor again, so 6 minus 3 minus 1 is minus 4. Okay, let's go f triple prime. So it's 6 times minus 4 is minus 24, but the minus 1 factor comes out from the chain rule. Minus 4 minus 1 is minus 5. Okay, let's go one more. 24 times 5 is 120. So this is going to end up being positive 120. And then minus 5 minus 1 is minus 6. Okay, so now for each of these, we come to the right column. And you make a little more room on the left column because you're doing the whole derivative of the function. Here we're just going to plug in the center point. So each of these is going to be a Maclaurin series. So it's going to be 0, 1 minus 0 squared, so 1 f. Okay, 2. So it's just going to be, each of these is just going to be whatever the numerator is. Okay, so next what you do is you just take a glance at the numbers here and see if just at first glance do you see a pattern. If there's an obvious pattern, then you could come straight to the coefficient, the c sub n. So the c sub n is f, and so it's going to be centered at 0. And so the idea is if this is these are the f to the nth derivative of 0. So if you see a pattern here where you can create an n formula for this, then just go ahead and create the formula and stick that in the numerator and over n factorial, and there's your c sub n. But here there's not an obvious pattern, so we still could potentially dig into this and find one, but since there's not an obvious pattern, let's go ahead and actually come to another page and apply the n factorial to these and see if that reveals a pattern. Okay, so we had f of 0. So yeah, the 0th derivative that's considered the function. So n starts at 0. The 0th derivative, that's the function itself. So that was 1. And then f prime of 0 was 2. Let's see. 6, 24, 120. F double prime, 6. Okay, so let's divide each of these by n factorial. So here we've got 1 over 0 factorial. 0 factorial is 1. Okay, here we've got 2 over 1 factorial. So like this is to the 0th derivative. This is the first derivative. That's the n. So this is 2. Here we've got 6 over 2 factorial. That's just 2. So this is 3. Here we've got 24 over 3 factorial. That's 4. And then here we've got 120 over 4 factorial. So 120 divided by 2 is 60. 60 divided by 3 is 20. Okay, and there you go. You see, now we can see a definitive pattern. So sometimes you could see a definitive pattern just straight from the nth derivative of the center point. Or if you go ahead, if you can't find a definitive pattern there, go ahead and divide by n factorial and see what you get. So here we can see that. So this is c sub 0. This is c sub 1. Okay, so what is c sub n? Well, if n starts at 0, we see it's just going to be n plus 1, the entire c sub n. Right, n is equal to 0, we've got 1, n is equal to 1, we've got 2. So this is the entire c sub n, and the power series representation of a function. This is the c sub n. Okay, so that means that the f of x it's not equal to, but it's Maclaurin series representation is, so n plus 1 times x to the n. Okay, but now let's find the radius of convergence. And so with power series, the way that the form is set up for any power series is that the majority are going to work well with the ratio test. But if it's a rare case where the ratio test doesn't work, you can try the root test or just go to some other test. But in general, power series are all of the same general form, and it sets up well for the ratio test. So, okay. We've got the absolute value of a sub n plus 1 over a sub n. Okay. So n plus 1, that's n plus 2. Okay, then x to the n plus 1 is going to be x to the n times x. Okay, and we're dividing that by n plus 1. Okay. So we could take out the n plus 2 over n plus 1 is always positive. Okay, so, all right, there we go. So we need to take the limit as n goes to infinity of this. This is going to go to 1. And so that means that this approaches, the limit of the absolute value of a sub n plus 1 over a sub n approaches the absolute value of x. This passes the ratio test when this is less than 1, which means that this tells you that the radius of convergence is 1. Now, as far as the interval of convergence, testing the endpoints, we're not going to do that. I think that the textbook doesn't want to make these problems too drawn out and long. But yeah, in general, for like an real application, you'd want to fully understand your power series. So you'd go ahead and plug in r or x is equal to 1 to see what happens if it converges, and do the same thing with minus 1. But we're not going to go that far with these problems. Okay, let's find the Maclaurin series for cosine x. Okay, so start off with just f of x. Again, this is the 0th derivative. Is cosine x. F prime of x is minus sine x, and we're just going to go as far as we need to go to identify a pattern, or maybe identify that there isn't a pattern. Okay, so we've returned back to cosine x. So we can see if we kept going, it would start the same pattern again. So now let's plug in the center point. Cosine of 0 is 1. Sine of 0 is 0. Okay. So now here, this is a little different. So you think about, well, can we just go ahead and, if there's an easy pattern, or you get an easy n formula for this and just put it into the numerator here. It looks like we could easily get a formula, but it's a little tricky with these zeros because we're not going to be, these aren't going to be terms. We're not going to want, like, it's not like we're going to make a formula where we want the second or the first derivative, n is equal to 1 to be 0, right? So when we've got zeros like this, it's easiest, in my opinion, to go ahead and go write out the first 4 or 5 non-zero terms. Now you might be thinking, well, couldn't we just kind of skip this term and then, we're going to have get a pattern for this? It's going to be like minus 1 to the n or something. You could do that, but it gets a little bit, whenever you've got these 0 terms here, it gets a little bit tricky because then the n, you'll see. To me, I would say if you have 0 terms, just go ahead and go and write out the first full non-zero terms. So, okay, f of 0 is 1, and then f double prime of 0 is minus 1. Then the fourth derivative of 0 is 1. Etc. Okay, but now let's divide each of these by n factorial. Okay, so we'll just leave the factorial. So we've got okay, so but now we can see, we can write what the c sub n will be. So it's going to be 2n factorial and then minus 1 to the n, because we start positive, we start n is equal to 0, and then you have 0 factorial, and then n is equal to 1, 2 factorial, n is equal to 2, it's 4 factorial, etc. Okay, so now let's write out the Maclaurin series, but there's another thing that you don't want to forget about when you've got 0 terms like this is, so, okay, here's the c sub n, is you're going to need to update the exponent on the x. We can't just do x to the n. Why not? Because when the coefficient is equal to 2, we skip the first term. So if we did just n, then whenever n is equal to 1, we'd get the right c sub n, but then we have x to the first power. It's x to the second power. So we need to do x to the 2n. There we go. Okay, now let's find the radius of convergence. Okay, the minus 1 to the n goes away. So x to the 2 times n plus 1, that's x to the 2n plus 2. So we've got x to the 2n times x squared. And then over 2n plus 2 factorial. Okay. Then x to the 2n. Okay. So now we can write 2n plus 2 factorial as okay, so now, okay, so we can take out this 2n plus 2 over, times 2n plus 1 is always positive. Okay, so now there's the absolute value of a sub n plus 1 over a sub n. As n goes to infinity, this goes to 0, so this is 0 for all x, which is always less than 1, so the radius of convergence here is infinity. Okay, let's do 2 to the x. So we've got f of x is equal to 2 to the x. So we're trying to find that Maclaurin series for 2 to the x. So f prime of x, what is the derivative of 2 to the x? Well, exponentials with bases other than e, well, all exponentials, it's you just rewrite the exponential and then natural log of the base. So if the base was e, then this is just 1. Okay, so f double prime is, so it's just going to have another natural log of 2 come out. Okay. Okay. So now we plug in the center point. 2 to the 0 is 1. And we can see that it's just going to be, each time it's going to be that factor. Okay, so now here's an example where we can see just glancing at this, we see a clear pattern. So what we can do is we come to the C sub n. This is the nth derivative evaluated at 0 over n factorial. So we see it. We can get an n formula for the nth derivative evaluated at 0 easily here. We just say natural log of 2 to the n. Starting at 0, you get 1, then n is equal to 1, etc. And then with that, we have over n factorial, and there's C sub n. Okay, so we've got 2 to the x power. Its power series is, and then just x to the n, because we haven't lost any terms. Okay, let's get the radius of convergence. Okay, natural log of 2 to the n plus 1 is natural log of 2 to the n, natural log of 2 over, or no, times x to the n plus 1. Okay, n plus 1 factorial, let's go ahead and write it like this. Okay, so now we've got natural log of 2 to the n. Okay. There we go. Okay. So this is natural log of 2 over n plus 1. Okay, we can take out the natural log of 2 over n plus 1. That's always positive. Okay, so what is the limit as n goes to infinity of this? Well, natural log of 2 over infinity, that goes to 0, so this is 0 for all x, which is always less than 1, so this radius is infinity. Okay, let's find the Maclaurin series for hyperbolic sine. Now, remember with the hyperbolic functions, the derivatives are similar to the derivatives of trig functions. So we've got f of x is equal to the hyperbolic sine of x. And then actually with derivatives of hyperbolic sine and cosine, they're actually simpler than trig functions. So that's the same, but then when we do the derivative of hyperbolic cosine, it's just positive hyperbolic sine. So there's the pattern right there. We actually could have just stopped. We could have just stopped here. Okay, so let's plug in 0. Let's see what we have. So, okay, hyperbolic cosine of 0 is 1. And then hyperbolic sine is 0. Okay. So 0, 1, 0. Okay, so we've got here, once again, we've got these 0 terms. So let's go ahead and go to the full coefficients. So, okay, f, what do we have? Okay, so it's f prime of 0 is 1. F triple prime of 0 is 1. F to the 5th of 0 is 1. Okay, so 1 divided by 1 factorial. So yeah, let's just write it out. So 1 divided by 1 factorial, 1 divided by 3 factorial, 1 divided by 5 factorial, 1 divided by 7 factorial. So there, now we can see the C sub n pattern. We're going to have, so 1 in the numerator, and then in the denominator it's going to be, so we're starting at 0. So let's see, it would be 2n plus 1 factorial should be it. N is equal to 0, we got 1 factorial, n is equal to, okay, no, that's not it. Because n is equal to 3, we've got 7 factorial, so okay. Oh, no, I'm sorry, that's right. N is equal to 0, you've got 1 factorial, n is equal to 1, 3 factorial, n is equal to 2, 2 times 2 is 4 plus 1 is 5 factorial. Yeah, that's right. Okay. So now let's write out the Maclaurin series. But just remember, when you've got missing terms, 0 terms, you're going to need to update the exponent on to the power of x as well. So, okay, 2n plus 1 factorial, and then it should just be x to the 2n plus 1. So at n is equal to 0, you got 1. N is equal to 1, you've got 3. N is equal to 2, you got 5, etc. Okay. Okay, let's get the radius of convergence. So we've got, let's see, x to the 2n plus 1. So 2 times n plus 1 plus 1. That's 2n plus 2 plus 1. 2n plus 3. So x to the 2n plus 3, let's write that as x to the 2n times x cubed. Okay, and then we've got, this is going to be 2n plus 3 factorial. Okay, then x to the 2n plus 1, and then 2n plus 1 factorial. So we've got 2n plus 3 times 2n plus 2 times 2n plus 1 factorial. That's how we can write 2n plus 3 factorial. X to the 2n times x cubed. And then okay. So we've got 2n plus 3 okay, so we can take out, this is always positive, we can take this out of the absolute value. Okay, there we go. There's the absolute value of a sub n plus 1 over a sub n. We take the limit as n goes to infinity of this. This term goes to 0, so for all x, this is equal to 0, which is always less than 1. So the radius of convergence is equal to infinity.